Woohoo! We're on lecture 10, you guys, or chapter 10, lecture A. To be on chapter 10 is awesome. That means we only have one more chapter to go and we don't really cover chapter 11 in much depth. So I'm going to go through lecture A. We'll probably add an additional lecture. And yeah, that's about it. Let's go ahead and get on it. So valence electrons. Valence electrons, the reason we care about valence electrons or even talked about valence electrons is because they're the electrons that do chemistry. They're the things that bond, that allow reactions to occur, etc. In order to learn what molecules look like and how valence electrons are available, etc., we're going to learn how to build structures. We're going to build Lewis. It's called Lewis structures. Lewis structures show, I probably should have written this, Lewis structures show bonding. So they show bonding, and they also show non-bonding electrons. And if we have a structure and we're able to see what was bonded and what's available as a non-bonding electron, we're able to figure out a lot of stuff about chemistry. All right, so in order to understand it, we need to know electronegativity. If you remember, electronegativity is things that going up and to the right is more electronegative. And I generally, about this time in our class, I would have a slide that says the most electronegative element is fluorine, because we don't include noble gases. These are excluded. They don't need to bond with anything. So they're totally happy they've got their 8 valence electrons. And then I'll say the most electronegative element is fluorine. Seriously, the most electronegative element is fluorine. And then I'd ask an iClicker question, hey, what's the most electronegative element? And you ought to say fluorine. Fluorine really loves electrons. That's also what makes it real small. And yeah, let's go ahead and use that information to help build structures as well. We need to know about counting valence electrons. We'll get into that here after this. We need to understand octets, and eventually we'll get to formal charges to understand the most stable structures. All right, so let's start with counting valence electrons. You already have a pretty good idea about this. If you remember, this is column 1, this is column 2, 3, 4, 5, 6, 7, 8, and the column that it's in tells you the number of valence electrons. When we're talking about drawing Lewis structures, we're only going to be discussing pretty much non-metals stuff over here, because we're talking about molecular compounds or covalent compounds, so we're only talking about mainly non-metals over here. All right, so how many valence electrons are in carbon? Well, you'd simply look at it and see that it's in the 4th column, and your answer would be 4. And we could know that if we went through and did the electron configuration for carbon, but I think just having that general idea doesn't make it any more confusing. It's probably simpler that way. All right, oxygen then is right here in the 6th column. It has 6. And that same principle applies for molecules. So here we have carbon dioxide. That's a carbon plus 2 oxygens, right? And if I want to know the number of valence electrons here, I'd say, okay, well, that's 4 plus 2 times 6. And this would be 12 plus 4 is 16, I believe. All right, now we get to something like carbonate down here, a carbonate ion. It's got carbon plus 3 oxygens, but it also has a 2 negative charge. This tells you there's 2 additional electrons. Now here's something I thought about after I already wrote this worksheet. If you're paying attention to this, I want you to, whenever you're counting valence electrons, put the charge first. So make sure you don't forget that, because it's really easy for you to do, really easy for me to do. So I look at this carbonate ion, the first thing I say is, hey, there's 2 extra electrons, plus the carbon, we get 4 from carbon, plus the 3 oxygens. Each one of those is 6. And then you can add them up. Essentially, it looks to me like we got 4 times 6, or 24 valence electrons from that CO2. All right, so now I want you to go ahead and pause and try to do these. If you don't, that's cool, but you ought to be testing yourself every step of the way here. So how many valence electrons are in nitrogen trioxide? That's NO3. Nitrogen here has 5, and oxygens again have 6. So we'd be looking at 5 plus 3 times 6, 5 for one nitrogen, plus 3 times 6 for the oxygen. And that would give me a total of, what's that, 18 plus 5 is 23. Now, one cool thing about Lewis structures, I don't know if you can hear my dog eating. It's funny, whenever I start filming a video, they decide to eat. They don't eat all day, then I film a video. Okay, so if you're doing this and you get something like 23, when you're drawing Lewis structures, this is an odd number. You pretty much won't see that in drawing Lewis dot structures. You can get into that more in organic chemistry, but right now, if you get an odd number, chances are something either went wrong or you're not going to be able to draw the Lewis structure. However, let's look at nitrate. That's NO3 negative. Now, according to our rules, the very first thing we should put is that 1 electron plus 5 from the nitrogen plus 3 times each of the oxygens, and that will give us 24, and that's looking a little bit better. We can draw a Lewis dot structure with an even number, so woohoo, woohoo, cool. All right, so let's move on to the next topic. We said, if you remember up here, it said we got to talk about electronegativity, which we already understand a little bit about. We're going to talk about counting valence electrons, which we already now know about. Now we're going to talk about octets. Okay, octet, oct meaning 8, is when you have an atom that has 8 things around it. By things, I mean a dot is going to count as 1 thing, and a bond is going to count as 2 things. Bonds are represented by those lines that you see. So here we have this boron trifluoride. I asked you, does boron have an octet? Well, boron has 1, 2, 3 lines. Remember, each line counted as 2. So 1, 2, 3, it's got 2, 4, 6. And last time I looked, 6 things does not equal 8 things. So this boron does not have an octet. And right now we're just getting used to what an octet is. There's nothing wrong or great about it, it just doesn't have an octet. Let's look at each of these fluorines. Now each of these fluorines is exactly the same. It has 1 bond and it's got 6 dots around it. So the question is, does that have an octet? Well, remember, each bond counts for 2. So this fluorine right here has 2 from the line and then each of the dots. Another way might be to look at each of the dots. 1, 2, 3, 4, 5, 6, plus the line gives you 2 more. So 1, 2, 3, 4, 5, 6, 7, 8. This thing has an octet. Yes, octet. Does the hydrogen have an octet in this situation? Well, it only has 1 line, so it only has 2 things, or 2 electrons, as we'll come to know. And so this is no. Will hydrogen ever have an octet? No. And here's why. Let's look at hydrogen. So, I didn't really want to go off on this tangent, but I think it will help in the end. So let's look at hydrogen. In electron configuration, hydrogen is a 1s1. So that means it's got 1 electron in its 1s orbital. How many more electrons can it accept? Just 1. It's not 1s, it doesn't go over to 2s or 2p, etc. It can only accept 1 comfortably. And that is why it can only hold 2 electrons. It only wants 2 electrons. So anytime we have a bond, what we're representing is 2 electrons. Now let me take it a step further, and let's look at carbon. So carbon, if you remember, has 4 valence electrons. So let's go ahead and draw those. 1, 2, 3, 4. Hydrogen has just 1 electron. In order to make a bond, essentially these electrons share. So carbon here can make 1, 2, 3, 4 bonds, and that's why it will react with 4 hydrogens and share these electrons. Another way to even look at it would be to look at carbon's electron configuration. Carbon's electron configuration after helium, its valence electron configuration, is 2s2, 2p2. So how many more electrons can carbon accept? 1, 2, 3, 4. Before it's like a valence, and that's why it likes to make 4 bonds. So kind of a tangent, but hopefully it ties together the fact that when we're talking about a bond, we're talking about sharing an electron here. We're talking about 2 electrons. Okay, so back to the task at hand. So does hydrogen have an octet? No. Will it ever have an octet? No. It's always only going to have 1 bond, and that's just the nature of hydrogen because it can't expand into the 2s or 2p orbitals. Okay. Carbon, though, here, does it have an octet? Well, we already talked about carbon wanting 4 bonds, but another way to look at it is just count. So it's got 1, 2, 3, 4 lines. Each line counts for 2 things, 2, 4, 6, 8. It has 8 things, or 8 electrons, and carbon does have an octet. Let's look at nitrogen. Nitrogen has 1, 2, 3 bonds on it. It also has these 2 dots over here. So 2, 4, 6, 7, 8. Nitrogen also has an octet. Let's move down here. Here we have nitrogen again. It has 3 hydrogens on them. Again, the hydrogen only has 1 bond. It's never going to have an octet. And this nitrogen has 2, 4, 6, 7, 8. This also has an octet. Notice some similarities in the nitrogen here. Here we have a nitrogen with 3 bonds and 2 dots. Here we also have a nitrogen with 3 bonds and 2 dots. And we'll get to the reason here in a second. Actually, right about here. So when we're making Lewis structures, we're going to follow a few rules. Step number 1, we're going to count valence electrons like we have been. Step number 2, we're going to look at the periodic table and put the least electronegative atom in the center. Remember, it goes up and to the right on the periodic table. You exclude noble gases. Another way to look at it is usually the first atom written is most electronegative. Usually En represents electronegativity. All right, then we put the things together. H is always going to be on the outside. It only makes 1 bond as discussed. All other bond numbers can usually be relatively predicted from the periodic table, which is kind of cool. Carbon, as we discussed, makes 4 bonds because it wants 4 electrons to be like a noble gas. Nitrogen makes 3 because it wants 3 electrons to be like a noble gas. Now let's pull this down so we can make sure we really understand this concept. So here we have carbon. It's 1, 2, 3, 4 away from a noble gas, so it makes 4 bonds. Nitrogen, it's 3 away from a noble gas, so it makes 3 bonds. Oxygen's 2, so it makes 2. Fluorine is only 1, so it makes 1. We'll eventually get to some other rules of things down here after the 3rd row can accept more and do some really weird stuff, but generally carbon, nitrogen, oxygen, and fluorine are pretty much always going to be 4, 3, 2, and 1. When they're not, they tend not to be stable. All right, the oxygen rule, or the octet, rule usually applies. We'll talk about exceptions later. Today is not the day to do it. Let's get a good idea for how to do these things. All right, let's go ahead and start with example 1. I ask you to draw the Lewis structure of this duty bopper. Well, again, we want to go through the steps that we just discussed. Step number 1, let's go ahead and count valence electrons. So here we have a carbon plus 2 chlorines plus 2 fluorines. Each carbon is 4 plus each chlorine is 7 plus each fluorine is also 7. It looks to me like this is going to be 28 plus 4 is 32 valence electrons. Then it says, which is the least electronegative atom? Well, true to form, it's the one that comes first. But another way to look at it, just to make sure we understand electronegativity, is again going up and to the right. This one's the most electronegative. So carbon's pretty far from fluorine. Chlorine is really close to fluorine. That's why carbon is the least electronegative. So carbon So we're going to put carbon in the center, and we're going to put things around it. It says, how many bonds does carbon want to make? Well, carbon's got 4 valence electrons. It needs 4 more. You also wrote it right here that it wants to have 4 bonds. And so it helps to draw those bonds out, fill in everything that you can, and then go back and we'll count and make sure everything works out. Okay, so we added 4 bonds to carbon. Do you remember how many bonds chlorine and fluorine want to make? They each want to make just 1 bond. So sometimes it helps to just draw them out, or sometimes it comes more intuitively that if chlorine or fluorine only wants 1 bond, then you just put a chlorine there and fluorine there, because again, we need 2 chlorines and 2 fluorines, and we're good. You don't need to, we're good so far. You don't need to worry about these flipping around. We'll get into when it matters where you put things, and when it matters where you put things is when you have a double bond somewhere, or a triple bond. Okay, so now we're good, but it says fill it all in and check the octet. Well, there's a few things we want to do. We want to make sure we have an octet. And number 2, we want to count valence electrons. These kind of go hand in hand, because in making sure that this has an octet, you look at this chlorine only has 2 things. So it doesn't have an octet right now. And we want everything to have an octet, because the octet rule usually applies, and we're not talking about exceptions yet. So when we look at this chlorine, we're like, hey, this guy definitely needs more. And so does this fluorine, and so does this fluorine, and so does this chlorine. What about this carbon? Does this carbon have an octet? Well, it's got 2, 4, 6, 8 things around it. Carbon is actually good right now. That doesn't mean we don't change it, but that means we can kind of check it off our list for a second. All right, the other thing we want to do is count valence electrons. Well, each bond counts for 2 valence electrons, and dots count for 1. We want to get a total of 32. So if you count right now, so far we have 2, 4, 6, 8 valence electrons. That's hardly enough. So we'll fill in the octet and then count again and then adjust accordingly. So for chlorine to have an octet and still have 1 bond, we have to put 1, 2, 3, 4, 5, 6 dots around it. So that gives it 2, 3, 4, 5, 6, 7, 8 dots. You do the same for this one, the same for this one, the same for this one. And now everybody has an octet. Now we got to count the valence and make sure that they add up to 32. If they do, we're good. If they don't, we adjust. So let's start with the chlorine here. We've got 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26, 28, 30, 32. Everything has an octet. We have the appropriate number of valence electrons. We're good. This, in fact, is the structure, Lewis structure of this molecule. All right, let's have more fun. Okay, now we're going to draw the Lewis structure of this cool ion here. It says count how many valence electrons are in it. Now, you might not be able to see on the video very well, but this is a negative sign. That's really important that we pay attention to that. That's the one we put first. Remember, we count the charge first, plus phosphorus. If you look at phosphorus, it has 5 valence electrons. And then there's 2 chlorines. Each of those have 7. And that totals up to, what's that, 14, 19, 20. Now it says, which is the least electronegative? Well, chlorine's really close to fluorine. Phosphorus is a few away. Where chlorine is the most electronegative, and phosphorus is the least electronegative. Again, this molecule started with it, so that usually goes in the center. Now it says, fill it all in and finish with the octet. So we know how many electrons we need. Let's go ahead and start filling it in. Now you look at this and you're like, hey, phosphorus right here, it probably wants 3 bonds because it's like nitrogen. But if you remember, I said things in the third row and below are kind of funky and not always the same as what you'd think. But what we did go over is chlorine usually likes one bond. So let's go ahead and give chlorine one bond. You could have tried to give phosphorus 5 bonds. You would have had like a triple bond here and a double bond here. It would have taken all day, but you can do it using the rules that we're using here. Once you've bonded things together, fill in the octets. So chlorine here would be 1, 2, 3, 4, 5, 6, and then it's got this 7, 8 from the bond. Phosphorus here already has 1, 2, 3, 4, so it needs 4 dots on it. Where you put the dots doesn't not matter. It doesn't have to be pretty, it has to be right though. And then we move on to chlorine here. As chlorine's attached here, it's got 1, 2, so we need to put 1, 2, 4, 5, 6. Okay, so if you remember, first we fill in the octets, then we check for valence. We need 20 electrons, and if there aren't 20 electrons, we'll figure it out from there. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20. I've got 20. We are done. All right. Moving on to the next one. It says draw the Lewis dot structure of this thing. This is methanol. It says hydrogen will always go blank. Hydrogen will always go on the outside because it can only have one bond, so it can't ever go in the middle because then it'll have to be bonded between two things. It can only ever have one bond, so it will always go on the outside. That's a helpful information, especially when you come to draw this. All right, we look at carbon, or well, let's first count valence electrons. So we've got a carbon, which has 4 valence electrons, plus 4 hydrogens, plus the oxygen. To me, that looks like 14. So we need to end up with 14 electrons. Let's draw this thing. We know that carbon likes to make 4 bonds. But there's 5 things here. Hydrogen, 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 and oxygen. If you start by saying hydrogen, 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 if you were to put a hydrogen here, in fact, let's do it. Is there any way you can add an oxygen anywhere and not break the octet for carbon? Remember, carbon right now has 2, 4, 6, 8. If you happen to add an oxygen, now it's got 10, and we can't do that. That breaks the octet. So what we have to do, let's go ahead and draw it again. What we have to think about is that hydrogen must go on the outside. So this carbon has to be bound to an oxygen somewhere. And then we can put the oxygen on the other side of that hydrogen. Now we can go back and fill in the octet and then count valence electrons. Carbon again has 2, 4, 6, 8. It's good. Oxygen right now only has 2, 4. So it needs 2 more pairs of electrons. So now oxygen has an octet. Now let's count and see if it adds up to 14. And if it doesn't, we'll adjust from there. Here we have 2, 4, 6, 8, 10, 12, 14. And it looks to me like we're good. Woo! All right. I didn't leave much room here. I don't know what I was thinking. But it says, I'm actually going to move this to the next page, but we'll get there. I'm going to use this space for the next one. So draw the Lewis dot structure of C2H4. Cool. Let's do it. Let's start by counting valence electrons. 2 times 4 for the carbon, plus 4 times 1. That looks to me to be 12. Electrons is what we need to end up with. All right, let's go ahead and draw it. We got a C and a C. Wait, what is going on? We have to find a way to put these on the outside. So it looks to me like we might not just have one single central atom, kind of like up here. So I can't just put a hydrogen between these two things. I have to put the hydrogen on the outside. And you could maybe put 3 hydrogens over here and then 1 hydrogen over here, but that's you'll eventually figure out that that won't work. You can't fulfill an octet. So when you have a number like this, like 4, try to equally share it on both sides, and then if you need to adjust, go back. So here we have H, 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 and let's go ahead and bond that carbon. Now it says fill in the octet. So if we're looking at carbon here, we've got 2, 4, 6, it needs 2 more electrons. Well, let's go ahead and try it. Let's put 2 electrons there. Let's follow the rules that we've been talking about. And then we go over here, we've got 2, 4, 6, and we'd have to put 2 electrons there. And now we can go ahead and count and see if we've got 12. 2, 4, 6, 8, 10, 12, 14. Anytime you have more valence, you're going to add a double bond or another bond. So we have 14 right now, we need to have 12. So what you do is you take these guys away and you add another bond there. And that makes carbon happy because carbon likes to make 4 bonds anyways. And some of you might have gone straight to doing that, but I want to follow the same process every time. So now if we look at this, we've got 2, 4, 6, 8 on this carbon. We've got 2, 4, 6, 8 on that carbon. And we can count to see if we got 12. 2, 4, 6, 8, 10, 12. We are good. And this is the structure for this compound. Now, if your paper looks like mine, then great. I think the first time I learned to do structures, my stuff looked kind of like this. So like if you're doing anything that looks decent, you should be really proud of yourself. All right. Now the next question, which I'm sorry I didn't leave enough space on my worksheet, maybe I'll leave it for you guys, was draw the Lewis structure of N2. Well, to draw the Lewis structure of N2, we have to know that it has 5 valence electrons at nitrogen, and there's 2 of them, so we're looking at a total of 10 valence electrons. N2 is telling us that there's 2 nitrogens. And there's a few ways you could do this. You can go back and remember that nitrogen likes to make 3 bonds, or we could use the process we've been using and just see how it works. So let's put a bond between the nitrogens and fill in the octets. 2, 3, 4, 5, 6. 2, 3, 4, 5, 6. So now each nitrogen has an octet. But we need to see if it has 10 electrons. Well, here it's got 2, 4, 6, 8, 10, 12, 14. So if we take one of these away and add another bond, remember anytime we have more, we add a bond, then we're looking at this. And now we have 2, 4, 6, 8, 10, 12. So this had 14 electrons, no. This one had 12 electrons, no. And hopefully you're seeing a pattern. We had 2 more, so we took away a pair of 2 pairs and made a bond, and we went to 12. Now we got 12, we're going to take away 2 pairs, and then we'll get to 10. Here we have N, triple bond is N. To fill in the octet, you have to have 2 extra electrons. Now we got 2, 4, 6, 8 on each of them, and in total we have 2, 4, 6, 8, 10 valence electrons. And that's why this is a structure for N2. And it's what you're breathing in this whole time. More than 70% of the atmosphere is that molecule right there. Okay. Atmosphere, air, I should say. Okay, so now it says, remember from the last lecture, if you remember bond order, single bond is 1, double bond is 2, triple bond is 3. Let's look at this. What is the bond order of this N2? Well, it's got a triple bond, so the bond order is 3. Again, triple, 3. So this would be a relatively strong bond. If you remember, 1 is the least strong, up to 3 is relatively strong. Okay, let's go ahead and draw the Lewis dot structure of carbon dioxide. Carbon dioxide is CO2. At the beginning of this lecture, we figured out that the number of valence electrons were 4 plus 2 times 6, which is 16. And maybe by now you can see that carbon, maybe we can skip over some things and not follow the whole path. Carbon likes 4 bonds, if you remember, and each oxygen wants 2 bonds. So we put carbon in the middle. It's the least electronegative, is the farthest away from fluorine. And then we add oxygen. Well, I would normally put oxygen like this, but again, I know carbon wants 4 bonds and oxygen wants 2 bonds, so why not give them both what they want? Now we fill in the octet. And now let's count to see if they have the appropriate number of valence electrons. Here we have 2, 4, 6, 8, 10, 12, 14, 16, and we're good. Now what is the bond order of this thing of carbon-oxygen? It's going to be 2, because it's got double bonds. By now I think you're really getting it, hopefully, and if you're not, then go back and do it again and again. Now we're going to move on to ozone. I don't really tell you what ozone is. Ozone is O3. This is a common question I ask in lecture, and we get some really cool responses. This is not a cyclical Lewis structure. In fact, I haven't seen any of cyclical Lewis structures in any Gen Chem yet. But it is a regular structure, a linear structure of sorts, kind of like CO2 was here. So let's go ahead and figure out how many valence electrons it has. It has 3 times 6, which is 18 valence electrons. There really is no center, so you're just going to have 3 oxygens. Now, if we do something similar to what we did up here, you're like, hey, oxygen wants 2 bonds, right? But wait a second, what about that oxygen? It got 4. So that's kind of messed up. So we know nobody's going to be happy. There's no way you can do something that this oxygen's only going to have 2, and these oxygens are going to have 2. It's impossible. So let's go ahead and bond them, count valence electrons, do what we have been doing, give them their octets, and then figure out from there what needs to be double bonded, etc. Okay, so let's go ahead and give each of these oxygens an octet. So this one needed 6 because it's got 2, 4, 6, 8 now. This oxygen needs 2. These are called lone pairs, or 4 electrons. Here we have 1, 2, 3, 4, 5, 6. Okay, so now everybody has an octet. The question is, are there 18 valence electrons? 2, 4, 6, 8, 10, 12, 14, 16, 18, 20. No, there's 20. So what do? Well, anytime we have more, we take away 2 of these lone pairs and we build a double bond. So let's go ahead and do that. Like this. That one was still there. This has an octet. And now I took away one of them. I'll just kind of even them out. But essentially now we have 2, 4, 6, 8, 10, 12, 14, 16, 18. We have 18 valence electrons in this structure. Now you wouldn't be wrong, but why did I build it here? Why did I build a double bond here? Why didn't I build the double bond over here? Am I a jerk? It's against our class rules, but kind of. So was it fair, again, that we put the double bond on the right and not the double bond on the left? No, it's totally not fair. And this is where resonance comes in. This structure doesn't really exist, but neither does the mirror image of it. Neither of these actually exists. Instead, this oxygen is super happy, right? And this oxygen is super happy. And so what they're doing is they're playing tug of war. This one wants to be happy and this one wants to be happy. And they're actually sharing these electrons right here, moving back and forth between these. And when I say back and forth, I mean, I want to be very careful here because this question comes up a lot. It's not like it goes from here to 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 here. It's actually averaged, and these are spread out equally between these two things. And the way we represent that is with this. where this is like a dashed line, not a very pretty dashed line, let me make it a little bit prettier, where this is a dashed line representing that there is nothing that has a full double bond. These electrons are moving between here and here, and they're delocalized because they're not in one specific space. If something's localized, it's in one part. They're delocalized, they're spread across here, and this is a resonance structure. So I want to be really careful about how I lead up. So really, this is like an average of the two structures we did here. So one way to represent that a lot of people represent is with something like this, where we draw those two structures. And we say that these are in resonance with each other. Or we could just represent the whole structure. So you can give it in this brackets and say this is in resonance with this, or you can represent it like this. Personally, I prefer this because it makes more sense to me, that those electrons aren't in one part or the other. They're not moving back and forth. They're delocalized and they're hanging out, making all this as happy as it possibly can be. All right, so what is the bond order of this? Well, it's not 1, it's not 2, it's somewhere in between, right? It's actually 1.5. Let's take a step back and talk about why. Well, how many bonds do you have in total? Well, in total, you have 1, 2, 3 bonds. Shared between how many atoms? Well, it's shared between these two, that one and that one. In other words, you got 3 bonds per 2 atoms, which equals 1 1/2. If you didn't get that, just rewind it again and listen to it. But again, you look at the total number of bonds, divide by this many, and you get this. Once you hear that, drive this point home even more. Let's pretend that this is Johnny. Johnny has 2 friends. Sally over here. Sally's got short hair too. She's edgy. I like her. And Jack. Okay, Jack's bald. All right, and they each want an apple, but Johnny has 3 apples to give. They're not very pretty apples. They're organic. Don't judge me. Okay, so Sally and Jack each want as many apples as they can get, but Johnny only has 3. So what does he do? Well, he gives 1 to Sally, he gives 1 to Jack, and then he splits the other one in half and says you can have half and you can have half. And that's what happens. We had originally, if you remember, we had originally 3 bonds on this oxygen, and we want to share them with these 2 oxygens. So each oxygen gets 1.5 bonds. 3 things between 2 people. 3 bonds between 2 atoms gives you 1.5. All right, let's look at nitrate. Nitrate, we also talked about the bond, the valence electrons. Nitrate is NO3 negative, which tells us we'd want to start with that 1, or otherwise we'll forget about it. It's so easy to do. I do it all the time. Plus 5 from the nitrogen, plus 3 for the oxygens. That's 18, plus 5 is 23, plus 1 is 24. Let's go ahead and draw it. Here we have nitrogen. We're gonna put that in the center. It's the least electronegative. We'll draw the oxygens around it. Let's fill in octets. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6 now. And then 2 on the nitrogen, because nitrogen only had 2, 4, 6, so it needed 2 more to get 8. And now let's go ahead and count valence electrons. Well, now we have 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26. Oh no, we've got 26. What do? When we got more, we have to do a what? A double bond. So let's go ahead and do a double bond here. We'll get rid of this lone pair and we'll get rid of one of these. So now we're talking about N. And this should automatically give us 24. Hopefully we're getting to the point where we realize if we take away 2 lone pairs and make a double bond, it automatically reduces it from 26 to 24. But let's count 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, and we're good. Is this fair? No, because I could have easily chosen this oxygen or this oxygen. Here we have nitrogen. All these things are the same. So what's going to happen? The exact same thing that happened up here. This guy's going to share its 1, 2, 3, 4 apples with 3 different things. So you could draw it one of 2 ways. You could draw it in resonance, like we talked about, where we put a double bond here. In resonance with another one. Where the double bond was first on this one, then it was on the top one, now it's down here. We put a bracket like this to represent a charge. You put the charge outside of the bracket. It's got a -1 charge. So we can draw it like this, or we take an average of these structures, which is more likely what is actually being represented. And you can draw it like this, an N, O, 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 with that dashed line. Oftentimes people don't worry about the lone pairs when they're doing this dashed, because this gives a lot of information as is. You'd also, because it's a nitrate, you'd also put the charge on the outside, because it has a charge. So what's the bond order of this thing? Well, let's go back. This nitrogen had how many things to share? 1, 2, 3, 4. Across how many people, or how many oxygens? 1, 2, 3. So it had 4 things to share over 3 different atoms, which would be 1 and 1/3. And hopefully that makes sense. Every single one of them got 1, and then they had to share this extra 1 between the 3 of them. So they got even less apples, poor things. All right, so these take practice. Practice, practice, practice. You have it easy right now because I want you to go through and get a general idea of the rules and start practicing the rules. But when we get to the more complicated rules, we'll get into formal charge, we'll get into really understanding bond order, and we'll get a little more difficult here. Then I will provide you with a worksheet, and I want you to do that worksheet like your life depends on it, over and over and over and over and over again, please. And yeah, with that being said, y'all, I think I'm gonna go have an apple. Bye.